We're going to talk about multiple regression, which is an extension from simple linear regression. So let's start by reviewing the way that we've seen simple linear regression. The example I was using was trying to predict the volume on a rail trail, basically a bike path, based on the average temperature of the day. And the model that I fit using technology was 99.6 plus 4.8 times the average temperature. So this is a simple linear regression model because it has one predictor or explanatory variable. But there could be lots of other good predictors. So in the data set where I found this data, we have, of course, average temperature and volume, but we also have these variables spring, summer, and fall, which are zeros and ones, depending on whether it is a spring day. So these are not spring days. This row in the data set is a spring day, and this one is a spring day. These first two, it looks like, are summer days, and none of my first few rows were fall days. I have a variable called cloud cover, which is a measure of the amount of cloud cover. Larger numbers mean more clouds in the sky. That variable is measured in octas, which I'm not exactly sure what that is, but again, larger numbers means more cloud cover. Precipitation, that's the amount that it rained or snowed, and it's measured in inches. I've got a variable weekday, whether or not it was a weekday, and then again, my response variable, the thing that I'm trying to predict here is volume, the number of people that were on the rail trail on that particular day. Just take a second and try to guess which of these variables might be another good predictor for the number of people that are on the rail trail. Which one do you think would be the best predictor, maybe? So one way to determine what variables might be good predictors is to consider the correlation between the response variable and the variable that you're interested in. So the correlation between volume and average temperature is 0.43. We could round, and that looks like it is a really good predictor, or at least the best that we have here. And because it's a positive correlation, that means it's going to have a positive relationship with the response. And then we also have some variables like cloud cover where there's a negative correlation. So that means it's going to have a negative relationship with the response. But we're basically looking at the absolute value here. So the ones that have the largest correlations probably are going to explain the most variability in the response. So it looks like average temperature is probably a pretty good predictor. Cloud cover is kind of our second best. Then we've got things like whether or not it's fall and the amount of precipitation, whether or not it's summer, whether or not it's spring. That doesn't look like it actually helps that much. So these correlations essentially help us see if we were going to do simple linear regression, which of these predictors would predict the most variability. But we don't have to stick to just one variable. We can actually do a multiple regression model where we still have just one quantitative response variable, but we can have more than one explanatory variable. And we can call these different variables x1, x2, x3, all the way up through x sub k. That's the kth variable. And if we were going to think about the model in the population, it would be y is equal to beta 0, that's the intercept, plus beta 1 times x1, plus beta 2 times x2, plus beta 3 times x3, plus beta 4 times x4, all the way out to beta k times xk, and then plus epsilon. And those are the little residuals, the errors, the difference from our model predictions. So these are the parameters, the population parameters. And once we have a regression model, there's a few things that we might want to do with it. One important thing is to describe the relationship. And so this would be using the fitted coefficients like B0, B1, B2, all the way up through BK. We also might want to know if the model is good. And by that, I mean like if the predictors are significant, see what percent of the variability is explained, see if it makes sense. There's a lot of things that we can do to sort of decide if the model is a good model or not. So let's start with getting the coefficients. So we have our population parameters, which we're never going to be able to actually find. But then we can use our sample data to calculate sample statistics. And I would use technology like R or Minitab, something like that, to find the fitted regression coefficients. So we use letters like B0 and B1 to denote the sample statistics that are the coefficients on our different variables. And those B coefficients go up to B sub k, and then the piece that's not here on the end is that epsilon. So we don't have errors when we're looking at our fitted y-hat model. Here is some output from R for using both average temperature and cloud cover as predictors of volume. So we decided that those look like our two best predictors, and so we're going to use them both as predictors. There's a lot of stuff in the R output. The part that you really want to focus on is right here. And I think on my next slide, I've actually just kind of focused in right on that piece. So this has my estimate. These are my coefficients. Here's my B0. Here's my B1. Here's my B2. So I have the same information in a little bit neater table right here. So I could write out the model. It's going to be volume hat because I'm predicting the number of people, the volume on the rail trail. It's going to be 161.9 plus 5.5 times the average temperature minus 17.4 times the cloud cover. So this is a little bit more complicated equation than we've seen before. We still have our intercept, but now we have kind of a slope for each of our predictor variables. So we have this positive slope in the av temp direction, we have this negative slope in the cloud cover direction. And just like before, we can do predicted values. So what would the model predict for a 60-degree day with cloud cover of 7.9 octas? So let's plug in 161.9 plus 5.5 times 60 minus 17.4 times 7.9. So that's 161.9 plus 330 minus 137.46, or 354.44. And I'm just going to round to 354 because we can't have a partial person. So we would predict that there would be 354 people out on the rail trail on that day. That would be my predicted value. I could also do a residual if I wanted to. And remember, the residual is the observed value minus the expected value. So I would have to have given you the actual number of people who were on the rail trail on a 60-degree day with cloud cover of 7.9. And it looks like I actually had a day like that where there were 514 people. So if I wanted to do the residual 514 versus the predicted 354 or 160. So we under-predicted there. We have a positive residual. So this is just an extension from the simple linear regression. We're plugging in more numbers, but otherwise we're finding our predicted values and our residuals just the same way.